Energy, work, and power are terms used interchangeably by most people, but not by physicists. Let's explore the characteristics and differences of these three concepts so you can impress your family and friends. Oh, and we'll need to know about force as well. Hang in there, this will be a little complicated. I'll use as many examples as I can to make this easy to understand. Many physicists like the classical definition of energy. That's because for them, work and energy are nearly identical. They use the same units to measure both. To show this with Venn diagrams, you could move the yellow circle to overlap the blue circle to make one green circle that represents both energy and work. Now, if you prefer our working definition of energy, that energy is the ability to do work, produce change, and sustain life, then you can think of work as a subset of energy, and that's okay too. The units used for work and energy help explain their connection and give us insight to the definition of work. Physicists use an equation to define work. Work equals force times distance if the object the force is applied to moves in the same direction as the force. That's why the unit of work or energy in the American system is a foot-pound. You use a foot-pound of energy if you lift a pound of hamburger 1 foot. You could illustrate a foot-pound of energy with your students using a pint of milk or water. A pint is 2 cups, or 16 ounces, or a pound. Better yet, use a pint of ice cream. Maybe you should pause this video and go do a work demonstration now by getting some ice cream out of the freezer. Here are some other things you should know about work. First, when you do work on an object, you change the energy of the object. If you lift the pint of ice cream 1 foot, you have increased its gravitational potential energy by 1 foot-pound. If you turn the container on its side and give it a push, you have increased its kinetic energy. The amount of work you do equals the increase in kinetic energy. Do more work, and you give the object more energy. Here is another thing you should know about work. Even though you apply a force to an object, if it doesn't move, you have done no work on it. If the ice cream container is frozen to the shelf of your freezer and you can't move it, all your force and effort has resulted in 0 work. You have not changed the energy of the object, but your personal energy levels have changed. All that effort must have burned up a calorie or 2, right? In the MKS, that's meters, kilograms, seconds system, the work units are named after James Joule. You use a joule of energy if you lift an apple 1 meter, or about a yard. The force needed to lift the apple was a newton, named after Isaac Newton, of course. A force is defined as something that causes a change in the motion of an object. You can think of it as a push or a pull. Have you heard the legend that Newton understood the laws of gravity when he saw an apple fall from a tree? Imagine him picking up an apple from the ground. He applies 1 newton of force through 1 meter distance. Sometimes we use the unit Newton meter, but it is the same as a joule. You can choose your unit based on your preferred scientist. Just about every student and teacher remembers Isaac Newton, but do you remember James Joule or James Watt? I discussed them briefly in an earlier lesson. I could tell you more about them here, but you'll remember them much better if you discover the information for yourself. So instead, I'll ask you to go online and find out a little more about them as part of our activity. The unit of work, called the erg, was not named for a famous scientist. Instead, it is from the Greek word ergon, which means work or task. A joule is a large unit, like a mile or a kilometer. An erg is a smaller unit, like a foot or a meter. The erg is based on units of centimeters, grams, and seconds. It is also a word used in crossword puzzles. So now you know the rest of the story about work. Let's explore power. One of the units of power explains how power is related to energy. Since energy is measured in joules, and a unit of power is a joule per second, power is the rate of energy use or production. The equation relating energy and power is power equals energy divided by time. This is clear to the mathematically talented, but let me show you what it means with some examples your students can understand. Before we leave this slide, note that some other units of power are horsepower, watt, and kilowatt. Let's consider automobiles. Which car has the most power, a VW Bug or a race car? The race car has more power because it can go the same distance faster, and it needs more gas. The sports car can have from 500 to 1,000 horsepower. The VW Bug had from 25 to 50 horsepower. Now let's consider light bulbs. Which bulb provides the most light, a 40-watt bulb or a 100-watt bulb? The 100-watt bulb is brighter. It produces the most light or energy over the same amount of time as the 40-watt bulb. The 100-watt bulb has more power. It also uses more energy. Now let's see how much energy the light bulbs use in 1 hour. If your driving speed or rate was 50 miles per hour, how far would you travel in 1 hour? To find the answer, you multiply the rate by the time. We do the same thing to find the energy used. We multiply the rate in watts by the time. The resulting unit is a watt-hour, which is another unit of energy. Our eyes tell us the 100-watt bulb makes more light or energy, and our calculations show this as well. Most homes have more than one light bulb. Let's see how much energy is used by 10 100-watt light bulbs that are turned on for 5 hours. For one bulb, the energy equals 100 watts times 5 hours, or 500 watt-hours. For 10 bulbs, the energy equals 10 times 500 watt-hours equals 5,000 watt-hours. Over a month, you would have your lights on for many more hours. We need a bigger unit to measure these larger amounts of energy. That is why we use a kilowatt-hour. 1 kilowatt-hour is the same as 1,000 watt-hours. The utility company charges you for the energy you use, so they use kilowatt-hours. Look for that unit on your bill. Now, why do you think the W in kWh is capitalized? We have been looking at power used, but we can also look at power produced. Small wind turbines like this one have about 10 kilowatts of power. How many 100-watt bulbs could they light? To find the answer, change 10 kilowatts to 10,000 watts, and then divide by 100. This is a nice-sized turbine to power a small farm. The big utility-sized turbines are rated at 1 to 3 megawatts. A megawatt is 1,000 kilowatts, so they can make up to 3,000 kilowatts of power. Bigger turbines capture more wind and make more energy. On this drawing, note the size of the 10 kW turbine on the right compared to the 1,650 kW turbine on the left. At the base is a truck for a size comparison. Just as there are many forms of energy, there are many other units of energy, but we can convert them for comparison, just like you can convert inches into centimeters. Why? Because they all measure the same thing, energy. Many teachers like their students to do conversions because they are good mathematical exercises. I won't ask you to make conversions. Your computer can do that for you. I want you to see that there is more to energy than just the ability to do work. This concludes our lesson, the last one for this unit. Your assignment is to do the assigned activity, take the quiz, and prepare for your unit test.